Hello and welcome to lesson number 9, rational functions and partial fractions. So to start, let's talk about what rational function is. So rational function. A rational function, let's say Rx, is any function that is Px divided by Qx, where Px and Qx are two polynomials. There are a couple of extra conditions. Here, the polynomial function Qx cannot be identical to the zero function. Is not identical to the zero function. If Qx was identical to zero function, then across the entire domain of x, Rx would be something divided by 0, which we cannot allow. So we have that Qx should not be identical to the zero function. Furthermore, the domain and range of Rx are only restricted when Qx is non-zero. So we have that the domain of Rx is when Qx is not 0. Again, for the same exact reason that when Qx is 0, Rx is something divided by 0, which we cannot allow, so that is not part of the domain. So Rx is only really defined for all values of Qx that are not 0, which means that if Qx is 0 for all x, Rx would be undefined for all x. So to avoid that, Qx is not identical to the 0 function, and furthermore, Rx is only defined for when Qx is not equal to 0. An example function of this would be something like, let's say, fx is equal to x plus 1 divided by x minus 1. Over here, because we have x minus 1 on the denominator, and x minus 1 could be equal to 0, specifically x minus 1 is 0 at x equals 1, the domain of fx does not contain the point x equals 1. However, it contains every other point, and this is a perfectly valid rational function for all the points other than that particular point at x equals 1. So, now that we know what a rational function is, let's try to go to partial fractions. Before we do that, I just want to show you that we can divide these things. For example, fx is equal to x plus 1 divided by x minus 1. Recall in the previous lesson how we discussed about polynomial division. To do polynomial division, we just try to see how many of the denominator we can take out of the numerator. In this case, 1 times x minus 1 is of course x minus 1. So if we could get an x minus 1 on the numerator, we can take it out. In this case, we can take one of those out, and we'll have x minus 1 plus 1 plus 1 divided by x minus 1. Taking this x minus 1 out, we can see we have 1 plus 2 divided by x minus 1. You can divide rational functions and make them simpler, that's correct. And we are going to somewhat use that ability in order to try to understand what partial fractions are and how we do partial fraction decomposition. However, this polynomial division is only going to be useful when we are going to talk about improper rational functions, which we will get to right now. So, in normal fractions, we have something called proper fractions and improper fractions. A proper fraction is something like n divided by m for n less than m. If we have this condition, then this fraction is called a proper fraction. Examples of this are 1 divided by 3, 2 divided by 7, and 5 over 9. These are all proper fractions because the numerator is less than the denominator. What we call an improper fraction is some, let's say, p divided by q, where p is greater than q, greater than or potentially equal to. Because these are called improper fractions, because there is a whole part that we can extract. There's an integer part from this fraction that we can extract out of the fraction. For example, the fraction 5 divided by 3. 5 divided by 3 has a whole part of 3 divided by 3 on the inside, which we can take out and write as 1 plus 2 divided by 3. An improper fraction can be written as some whole quotient plus a proper fraction. It can always be so. Similarly, if we take any other thing, let's say 23 divided by 7. 23 can be written as 21 plus 2. 21 is a multiple of 7, so we can write this as 3 plus, and then we're left with 2 divided by 7. Again, any improper fraction can be decomposed into a whole part plus a proper fraction. Similarly, when we talk about functions, what we mean by an improper and proper rational function is this. A proper rational function is px divided by qx, where the order of px, let's say px is order n and qx is order m, the order of the numerator is less than the order of the denominator, so n less than m. You will recall from the polynomials lesson when we divided polynomials, if the order of the numerator was less than the order of the denominator, it was impossible to divide. You will recall, if we had something like x plus 1 divided by x squared minus 2x plus 1, actually it's alright, we'll leave that as the example. In this case, there are no polynomials we can multiply the denominator by to get the numerator. So therefore, this was equal to 0 with remainder of the numerator, which is x plus 1. You'll recall this. So here the same exact logic applies. If we cannot decompose the polynomial's ratio, the rational function, into one extra polynomial plus another rational function, that is this time proper, then that original rational function itself is proper. This is the same exact idea extended to rational functions. If the order of the numerator is less than the order of the denominator, it is simply impossible to simplify the rational function into a polynomial plus a simpler rational function. So therefore, a proper rational function is a rational function that is already having order of the numerator less than order of the denominator, meaning we cannot simplify it into simpler rational function plus extra whole part, which in this case is a normal polynomial. An improper rational function, on the other hand, improper rational function is a function which I'll say, let's say Rx divided by Sx. Let's say this is order k and this is order L. If k is greater than or equal to L, then this thing is an improper rational function. And we can see that it's improper rational function because, similar to how improper normal fractions were decomposable into a whole part plus another simpler proper rational fraction, similarly with rational functions, improper rational functions can be decomposed into a polynomial, or what we call the whole part, plus a simpler proper rational function. Take for example x squared plus 3x plus 2 divided by x minus 1. This is an improper rational function because the numerator has a greater order, greater than or equal order than the denominator, meaning that we can divide this into a polynomial plus another simpler proper rational function. If we do that, in order to get x squared here, we need to multiply x minus 1 by x, which means we have x here. Then x times x minus 1 is equal to x squared minus x. So we need a minus x on the numerator. So taking that minus x out, we get a plus x, and the plus x plus 3x plus 2 will give us 4x plus 2 on the numerator and x minus 1 on the denominator. We can still divide this further. Dividing further, we can see that 4 times the denominator will give us the 4x on the numerator. So then we have x plus 4 plus a little bit extra. 4 times x minus 1 is 4x minus 4. We need to take a 4x minus 4 out of the top. Here we have 4x plus 2. To get a minus 4 out, we need to subtract 4 and add 4. Taking that subtracted 4 out, we have a plus 4 and a plus 2. So we have 6 divided by x minus 1. This is now a proper rational function because we can no longer remove parts of the numerator, parts of the denominator out of the numerator. So we have thus finally concluded that this is an improper rational function, and when we decompose it into its whole part or polynomial part plus its proper rational function part, we get a polynomial of x plus 4 and rational part of 6 divided by x minus 1. So here this is the idea. I hope you understand. A proper rational function is a rational function where the order of the numerator is less than the order of the denominator, meaning we cannot break it down into a whole or polynomial part plus another simpler proper rational function. An improper rational function, on the other hand, can be broken down into a whole part, or what we would consider a polynomial part, plus a simpler proper rational function. In the same exact way that proper and improper fractions could have been broken down, improper fractions can be broken down into whole parts plus proper fractions. So now let's consider how this relates us to partial fractions. I want you to first consider a simple case. Let's say we have a divided by b plus c divided by d. If we want to simplify this algebraically, we need to try to take a common denominator, which means the left function of a divided by b needs to be multiplied by d divided by d, and similarly the right side c divided by d needs to be multiplied by b divided by b in order to get a common denominator of bd. If we do that, we get a times d, or ad divided by bd, plus and then c times b, so bc divided by bd, and then adding the two together with the common denominator, we get ad plus bc divided by bd. This is not the production of partial fractions, it is in fact the opposite of producing partial fractions. Going in this direction is algebraic simplification. What we want to do is to go from this thing, this simplified algebraic expression, back into these. These right here are the partial fractions of this compound fraction that we have created here. These are the partial fractions on the left. We want to try to go from something that looks like this into something that looks like this. So here you can see on the right side the denominator has bd in it, which is a compound number which is made of simpler numbers b and d. And on the left side, when we make the partial fractions, we wanted something divided by b only plus something divided by d only. So basically what we wanted to do was to factorize the denominator on the right side and try to write something divided by one of its factors plus something divided by another one of its factors. If we had three partial fractions being added together, let's say a divided by b plus c divided by d plus let's say e divided by f, and we say this is equal to, I'll quickly do this thing. On the denominator we're going to have bdf, on the numerator we're going to have adf plus bcf plus bde, and then now that we have this, we have on the denominator three numbers multiplied together. Our goal was to factorize the denominator. If we want to go in the reverse direction, we need to factorize this denominator into those three numbers and then write something divided by one of the numbers plus something divided by another one of the numbers plus something divided by another one of the numbers is equal to the composite fraction we have on the right. This is the same exact thing that we try to do when we want to do partial fractions, except instead of dealing with just numbers, we're dealing with polynomials. Consider the function x squared plus 2x plus 3 divided by x minus 1, x minus 3 and x minus 4. Consider this for a moment. Over here we have a numerator of x squared plus 2x plus 3 divided by x minus 1 times x minus 3 times x minus 4. In this case, we have a clear factorization on the denominator. We have one factor of x minus 1, another factor of x minus 3 and another factor of x minus 4. Recall that our goal in partial fractions was to have this denominator, which is a compound thing, factorize it into its smallest components and then write something divided by one of the components plus something divided by another one of the components all the way down. So, considering that here, what we want to do is to write the thing on the left as something which we don't know yet divided by x minus 1 plus something which we don't know yet divided by x minus 3 plus something which we don't know yet divided by x minus 4. This is what we want to accomplish by making partial fractions. We want to find what three things of x minus 1 on bottom, x minus 3 on bottom and x minus 4 on bottom were added together to create the thing on the left. Now, these two things, the polynomial rational function on the left and the rational function's sum on the right, have to be equivalent to each other. If I replace this equal sign with a triple equals, what I mean here is that this thing is true for all x in the real numbers. It is an identity. The thing on the left is identical to the thing on the right, which is anyway what we want to find when we have partial fractions. We want to find not something that works for any one particular x, we want to find something that works for all x. So now, if the thing on the left is equivalent to the thing on the right, we need to have that all the coefficients of x terms, x squared terms, x cubed terms, all of that on the left needs to be equivalent to everything on the right. So, if I just casually multiply everything by this denominator here, let's see what happens. If we just do that, we get on the left x squared plus 2x plus 3 being equivalent to, and now multiplying all of these things on the right, we can see we have x minus 1 on the new denominator and x minus 1 times x plus 3 times x minus 4. So x minus 3 times x minus 4 being multiplied up. So then this x minus 1 will multiply to the right, will cancel with this x minus 1, leaving us with just x minus 3 times x minus 4 times this something. So we have x minus 3 times x minus 4 times whatever this something is, which I'll just leave as a blank for now. I'm not going to put a symbol there, I'll just leave it as blank. Plus, and then something else over here. So we have here x minus 1 times x minus 3 times x minus 4 divided by x minus 3. This x minus 3 would cut to this x minus 3, leaving us with just x minus 1 times x minus 4 times another something. And then finally, this thing. If we consider this thing, here this x minus 4 would cut to this x minus 4, leaving us with just x minus 1 times x minus 3 times another something. So we have x minus 1 times x minus 3 times another something. So now, if the polynomial on the left is equivalent to the polynomial on the right, we need to have that the order of the polynomial on the left has to be equivalent to the order of the polynomial on the right. On the left, the order of the polynomial is order 2, which means we have highest power of squared, which means on the right side we need to also have a power of square as the highest power. In this case, we have over here order 1 polynomial times order 1 polynomial times unknown order polynomial has to be equal to an order 2 polynomial. So we have order 1, and order unknown. Order unknown, I'll just put k. This thing multiplied together needs to be equal to order of 2. So in this case, recall that when you multiply orders of polynomials, the orders get added together. Order 1 polynomial times order 2 polynomial is equal to an order 3 polynomial. So if we're multiplying these three together, then 1 plus 1 plus k needs to be equal to 2. The only way this can happen is if k is 0. If k is 0, then the order of the third polynomial over here is 0, which means that the third polynomial is a constant. So what does that mean? It means that we have to substitute into here some kind of constant. We don't know what it is yet, but I'll just put an a into here. If this was a, then in our original expression over here, this was also a, so we have that. Similarly over here, we have order 1 polynomial here, order 1 polynomial here, an unknown order polynomial here. I'll just put L for now. But this multiplied together needs to at most be an order 2 polynomial. So the order of the last term here, considering the product, we have 1 plus 1 plus L being equal to 2, which means that L is 0, meaning that this second one is also of order 0 or just a constant. So that means over here, this thing over here is also constant. I'll put B for now as the placeholder for the constant. It means that over here, up in the above, this was also just a constant, let's say B. And finally, using the same exact logic, considering this thing, we will have order 1 here, and unknown order here, let's say M. 1 plus 1 plus M needs to be equal to 2, so therefore M is order of 0. If M is order of 0, that means this is a constant. Here I'm going to replace this constant with, let's say, C. So that means we have C here, and that means we have C here. So there was a more obvious way to do this, of course. If you recall, in polynomials, we had a division rule that if you have an order of 1 less than your denominator on the numerator, then it is no longer divisible, and thus we have to write it as just a remainder. The same logic actually applies here. Considering the bottom here, on the left hand side we had a order 3 polynomial because we had an order 1 polynomial of x minus 1 multiplied by an order 1 polynomial of x minus 3 multiplied by an order 1 polynomial of x minus 4, and 1 plus 1 plus 1 would be equal to 3, meaning that on the left hand side we have order 3, and above on the numerator of the left hand side we have an order 2 polynomial. So we have order 2 polynomial divided by an order 3 polynomial. So the overall order of the left hand side is order 2 divided by order 3, which means order of 2 minus 3 or negative 1, which means that on the right side we need to have the same thing. The order of all of these needs to be negative 1, which means that when we multiply this thing to this side, all of these orders multiplied by this thing needs to be equal to the order on the left hand side. So it's kind of obvious that the order of the top needs to be 1 less than the order of the bottom. If it's not exactly obvious to you, that's alright. Just consider that here we have order of unknown divided by order of 1 being equivalent to something of order 2 divided by something of order 3. So therefore, if this order is 1 less than this order, then the order of this needs to be 1 less than the order of this. This is all fine and all right when we have a proper rational function. In this case, you can see over here, this is order 2, this is order 3, which means we have a proper rational function. Where this fails and does something strange is when we have an improper rational function, which we will now take a look at. Let's take a look at the improper rational function x cubed plus 2x squared plus x plus 1 divided by, let's say, x minus 3 and x minus 2. Considering this case, if this is equivalent to something divided by, let's just put a dash here for something, divided by x minus 3 plus some other thing divided by x minus 2, we would then have something up here and something up here, and when we multiply the whole thing on the left by x minus 3 times x minus 2 and the right side also by x minus 3 times x minus 2, we would have x cubed plus 2x squared plus x plus 1 equal to some unknown thing over here times x minus 2 plus some unknown thing over here times x minus 3. If these two polynomials are identical to each other, I'll swap out this equal sign for an identical sign, then the coefficients of the x powers on the left should be equivalent to the coefficients of the x powers on the right. You can see here we have order of 3 on the right side, left side here. This is order of 3, meaning that on the right side we should also have an order of 3. In this case we have order 1 polynomial here and order 1 polynomial here. These are both order of 1. If these are both order of 1, that means we need to multiply by an order of 2 polynomial here and an order of 2 polynomial here in order to get the thing on the left hand side. So therefore whatever we have in here is of order 2 and whatever we have in here is of order 2. So you might think that due to this we would have an order 2 polynomial in here and an order 2 polynomial in here, meaning that this would have to be something like ax squared plus bx plus c, and this would have to be something like, not to reuse the same symbols, instead of putting ax squared plus bx plus c into this one, I'll put dx squared plus ex plus f here. So what I mean by that is that x cubed plus 2x squared plus x plus 1 divided by x minus 3, x minus 2. You might think that this would directly be equal to, let's say, ax squared plus bx plus c divided by x minus 3 plus dx squared plus ex plus f divided by x minus 2. And you would be right that this is equivalent on the left hand side and right side, but this is not the simplest form that we can write this in. Mathematicians like simplicity, and you can see here for these two rational functions that we have here, the numerator has an order which is greater than or equal to the order of the denominator. Recall from polynomials lesson that we can divide one function by another function given that the order of the numerator of one function is equal or greater than the order of the denominator of that rational function. In this case, we can actually divide this thing and write this in a simpler format containing some constant here plus some, actually in this case, because we have order of 2 on the numerator and order 1 of the denominator, when we divide the order 2 by order 1, we get an order 1 polynomial. So we actually can get out of this thing an order 1 polynomial out. So we can get a whole part or a polynomial part of, let's say, px plus q over here. Similarly over here we have order 2 polynomial divided by order 1 polynomial, so we can also get another order 1 polynomial out of this one, let's say rx plus s out of this. So here, because we can do that, we can actually extract whole polynomial parts out of this thing. We can actually write this thing in a different format. Because we can extract order of 1 polynomials out of here, we can write that this thing is actually equivalent to an order 1 polynomial plus, and then on top here we would have to be left with an order less than the order of the denominator. So here this would be order 0 divided by x minus 3, and then plus, we could do the same kind of decomposition over here. This could have been reduced by polynomial division into an order 1 polynomial plus an order 0 polynomial divided by this normal order 1 polynomial of x minus 2. This could have potentially been done. And in fact, in mathematics, when we are doing partial fractions, if we have an improper partial fraction, we want to do this simplification. We want to get only proper partial fractions on the right hand side. So let's say we do this. If we do this, we have that on the left hand side x squared plus x cubed plus 2x squared plus x plus 1 divided by x minus 3 x minus 2 is equal to an order 1 polynomial plus this thing plus another order 1 polynomial plus this thing. So in this case, we have an order 1 polynomial plus an order 1 polynomial. We would be able to write these two sums of order 1 polynomials as a single composite order 1 polynomial. This is of course possible. Recall, any polynomial plus another polynomial can be written as a single polynomial on its own. So this means that we could actually simplify this even further into just a single order 1 polynomial plus some order 0 polynomial divided by x minus 3 plus another simple order 0 polynomial divided by x minus 2. This is what we are expected to do, by the way, when we are doing partial fractions. We are expected to have only proper rational functions on the right side when we are doing partial fractions, and any whole part is expected to be excluded. So then, considering the two cases, if we have Rx is equal to Px divided by Qx, where Qx is factorizable into some other factors, which I'll just for now say that Qx is equal to x minus a1 times x minus a2 ... a bunch of factors. If we have that Rx is a proper rational function, meaning that the order of Px is less than the order of Qx, it would mean that there's no whole polynomial part, and we can actually write this thing as something divided by x minus a1 plus something divided by x minus a2 all the way along. However, if Rx is improper, what this means is that there's a constant or polynomial part that we can put outside of each of these fractions, and that means that we have some polynomial of order, and the order of this polynomial, if this above here is order n, let's say order n, and this polynomial is order m, then recall that the polynomial whole part will be of order n minus m. So here this thing is of order n minus m, there's an order n minus m polynomial here, and then plus something divided by x minus a something divided by x minus b is a1, x minus a2 plus all the way down. So this is the general summary of making partial fractions from proper rational functions and improper rational functions. For proper rational functions, it would be possible for us to have only something divided by x minus a1 plus something divided by x minus a2 all the way down for all the possible factors of the denominator. However, if Rx is improper, then we would have to have some polynomial part that is not a rational function, is just a polynomial, plus a bunch of rational polynomial parts where we would have something divided by x minus a1, something divided by x minus a2 all the way down. And it is important to understand that even though we can write any polynomial as a product of simple roots of x minus something plus x minus something all the way down, sometimes because those roots are complex, we do not do that. I'll give you an example. If I have, let's say, x squared plus x squared plus 2x plus 1 divided by x minus 3 times x squared plus x plus 1. In this case, x squared plus x plus 1 does have simpler factors. It has the factors, if you recall, of x minus negative 1 plus root 3i divided by 2 times x minus negative 1 minus root 3i divided by 2. These two are factors that we can factorize out from this x squared plus x plus 1. It is possible to do. However, we don't do it. I'm not really sure why. Probably because of it looks ugly, it's not elegant, it has complex numbers in it. So we try to not do that. However, it is possible to do that. And I would like you to note that it is always possible to decompose any polynomial into such simple linear factors. We don't do that, however. In this particular case, instead of writing this thing on the numerator and writing this as something, let's just say something divided by x minus 3 plus something divided by x minus this whole thing plus something divided by x minus and then this whole thing. Instead of doing that, what we actually write is that this is equal to something divided by just x squared plus x plus 1. This also has the repercussion of now we have something different that we have to put on the numerator here. In this case, we have a proper function. The order of the numerator is order 2 and the order of the denominator is order 1 times order 2, which is order 3. So we have order 2 divided by order 3, which means that this left side is order of negative 1, order negative 1, which means that everything on the right side needs to be order of negative 1. In this case, x minus 3 is order 1. So in order for the whole thing to be order negative 1, this needs to be order 0, which means this is just a constant. However, on the right side here, because we are not factorizing x squared plus x plus 1 into its most simple factors and instead leaving it as an order 2 polynomial on the denominator, if we want an order of negative 1 overall, the order of the numerator needs to be order 1. This needs to be order 1 so that we have 1 minus 2 equal to negative 1. So what does this mean? If the numerator is order 1, it means that this is not just some constant b, it is in fact bx plus c. It has to be an order of 1 less than the denominator. So we have this. And again, let's now consider the case when we have an improper function over here on the left hand side. Improper rational function on the left hand side. Again, we get something different. If we have, let's say, instead of this x squared, if I put just a simple x to the 4th here, plus 2x plus 1, divided by x minus 3, times x squared plus x plus 1. In this case, we have order 4 up here. Over here, we have an order. I'll actually write not with a vinculum. Vinculum, by the way, is this line here. Instead of with a vinculum, I'll write with a curly bracket. This is order 4. This is order of 1 multiplied by 2, so order of 3, which means we have an improper rational function of order overall 1, which means that on the right side, we would have to have a polynomial of order n minus m, which is 4 minus 3, which is 1. So we have order 1 polynomial of, let's say, ax plus b. This is an order 1 polynomial. Plus something divided by x minus 3. In this case, it's just a constant, so c. Plus, instead of again factorizing x squared plus x plus 1 into its real roots, its simplest roots, we just write x squared plus x plus 1. And now here, because we want the order of the numerator to be 1 less than the order of the denominator, this will end up being dx plus e. So here, I want you to understand that here in this case, even though x squared plus x plus 1 could be written in simpler factors, we do not do that. This could trip you up sometimes. Like for example, if you have x squared plus 1, x squared plus 1 is equal to x plus I times x minus I. We could simplify and factorize it like this. This is true if you look over here. X squared plus 1 be equal to 0 means that x squared is equal to negative 1, meaning that x is equal to plus or minus the square root of negative 1 or plus or minus I, which in that case gives us these two roots that I've written down here of x plus I and x minus I. But we don't do this. If you ever have a partial fraction with on the denominator x squared plus 1, we do not write this as x plus I times x minus I. Instead, let's say we just give an example of x minus 1 times this thing, and let's say we have x squared plus x plus 1 here. Here we have overall order of 3, here we have an overall order of 2. In this case, we have a proper rational function. So all we have to do is write that we have a divided by x minus 1 here, plus instead of factorizing this thing like this and writing some b divided by x plus I and c divided by x minus I, we just write bx plus c divided by x squared plus 1. Here we have order 1 polynomial divided by order of 2 polynomials, so there's nothing wrong here. We have this. So I hope you understand here, even though it is possible to factorize some of these polynomials on the denominator, we do not do it. I have also often seen if we have something like x squared minus 3, which is factorizable within the real numbers. X squared minus 3 is of course x plus root 3 times x minus root 3. Again, we do not factorize this. I'm not sure exactly why, probably because it's ugly or something, but this thing is possible to factorize within the real numbers. I'm not really sure why we don't do it, we just don't do it. So let that be a little lesson to you. If we ever have something that has ugly factors, I suppose that's probably the logic that they have when they make these papers. If you look at any paper, sometimes you can get something like this, which is factorizable within the real numbers, but they just don't do it. They just keep it as an unfactorized x squared minus 3 or something like that. So my advice to you, if you ever see something like this that is not factorizable in maybe the logic is whole numbers. If something is not factorizable in terms of whole numbers, then we do not factorize it. For example, here if we have x squared minus 3, this is not factorizable, maybe rational numbers, maybe that's the thing. This is factorizable into x plus root 3 times x minus root 3, but here the root 3 is irrational. Maybe that's the logic that they use when they avoid factorizing x squared minus 3 into x plus root 3 and x minus root 3. So what I mean by this is, if we have, let's actually copy the exact same thing. If we have x squared plus x plus 1 divided by x minus 1 times x squared minus 3, they would not factorize this as a divided by x minus 1 plus b divided by x minus root 3 plus c divided by x plus root 3. Instead of doing this, they would factorize this as bx plus c divided by x squared minus 3. They would leave it like this. So as a lesson to you, as a general rule to you, if you cannot factorize in terms of whole numbers a certain factor in the denominator, don't do it and just leave it in the partial fraction breakdown like this. So as a final exercise to help you understand how to actually do these partial fraction breakdowns, we will do some together, and then you can also find your own, or maybe just write down your own and try to factorize them and turn them into partial fractions. Let's consider a simple example. Let's say x squared plus 2x plus 1 divided by x minus 2 times x minus 1. So in this case, we have an order 2 polynomial on the top, order 2 on the top is the order of 2, and we have an order 2 polynomial on the bottom. Since the orders are the same, we're actually going to have an order of 2 minus 2 or order 0 on the outside. There's going to be a whole polynomial of order 2 on orders 2 minus 2 on the outside or order 0. So if this is order 0, it is simply a constant, which I'm going to write as capital A. Plus. And now that we've done that, we've dealt with that, we can now do our normal partial fraction thing, where we just construct rational functions where the order of the numerator is 1 less than the order of the denominator. In this case, we have a denominator of x minus 2 and another denominator of x minus 1 over here. Here we have order 1 over here, so we have order 0 on the numerator. Similarly, here we have order 1, so we have order 0 on the numerator. So the partial fraction decomposition of the thing on the left hand side will look like a plus b divided by x minus 2 plus c divided by x minus 1. So now, to find the a, b and c, what we are going to do is multiply both sides by x minus 2 and x minus 1. This is alright because x minus 2 and times x minus 1 is not equal to 0, because recall, for the rational function, the values for which the denominator is equal to 0 are not part of the domain. So we are totally alright in multiplying the whole thing by x minus 2 times x minus 1. In which case on the left hand side we get x squared plus 2x plus 1 equal to, on the right side we get a times x minus 2 times x minus 1 plus b times, in this case the x minus 2 cuts with this x minus 2, leaving us with just an x minus 1, plus c times, in this case x minus 1 cuts with this x minus 1, leaving us with just x minus 2. We have times x minus 2. So if the polynomial on the left is equal to the polynomial on the right, that means that each of the coefficients of the x squared, x and 1 terms, constant terms, should all be equal. So in papers and in practice, what you would do is simply write r and x to the r terms over here. We would say, comparing the x to the r terms, what we get. So in this case, we need r to go from 0th powers to first powers to second powers. So we need r equals 0, r equals 1 and r equals 2. R equals 0 corresponds to x to the 0 terms or constant terms. On the left hand side, the constant term is 1. So we have 1 equal to, and then it should be equal to the product of all constant, the sum of all constant terms on the right hand side. Because if the left hand side polynomial is equal to the right hand side polynomial, then coefficients of all x to the r terms should be equal. In this case, for the constant terms, we have a times negative 2 times negative 1. So a times 2, which is 2a. We also have b times negative 1 here, which is negative b. And we have c times negative 2, which is negative 2c. So we should have that 2a minus b minus 2c equal to 1. This is one simultaneous equation that has to be true. Similarly, comparing the x to the 1 terms or x terms, on the left hand side we have a 2x here, so that means the coefficient in this case is 2. 2 should be equal to the sum of all coefficients of x terms on the right hand side. In this case we have a times x times negative 1 and a times negative 2 times x, which is negative ax and negative 2ax, so overall negative 3ax. Meaning that the coefficient of x in that term is negative 3a. So we have negative 3a. On the next ones, we have just a b times x here and a c times x here. So each of those have coefficients of b and c. So we have plus b plus c. This is another simultaneous equation. Furthermore, finally comparing the x squared terms, on the left hand side, we have a coefficient of 1 because we have 1x squared. This should be equal to all the x squared terms on the right hand side. In this case we have a times x, so ax squared, the coefficient of that is just a, plus b times this thing does not give us any x squared terms. Similarly, c times this thing does not give us any x squared terms. So actually there are no other x squared terms, we only have a single a and a single 1 on the left side. So this gives us that a equal to 1. A is equal to 1. Substituting a equal to 1 into the other two simultaneous equations, we can see that 1 is equal to 2 minus b minus 2c, and also that 2 is equal to negative 3a, which is a is 1, so negative 3 plus b plus c. So now we have these two simultaneous equations, which I'm going to call now 3 and 4. If we add 3 and 4 together, we get something. Let's just try 3 plus 4. If we do 3 plus 4 on the left side, we have 3. On the right side, we have 2 and a minus 3, so that's minus 1. The b's cancel, so we have no b's. And minus 2c plus c will give us minus c. So we have 3 is equal to minus 1 minus c. So 4 is equal to negative c, meaning that c is equal to negative 4. Substituting c is equal to negative 4 into one of the above two equations will give us the answer we seek. Substituting it into 4, we can see that 2 is equal to negative 3 plus b minus 4. Taking this minus 3 and minus 4, which is minus 7, to the other side, we can see that b is equal to 2 plus 7 or 9. So we have that b is equal to 9, c is equal to negative 4 and a is equal to 1. What does this mean for us? It means that substituting those values into this equation, we will get that the left hand side is equal to the right hand side. So what that means is that x squared plus 2x plus 1, this thing, divide by x minus 2x minus 1, which I'll write right now. X squared plus 2x plus 1 divide by x minus 2, x minus 1. This whole thing on the left hand side is equal to everything on the right hand side. Everything on the right hand side is simply a equal to 1. So we have 1 instead of a here. Over here we have b divided by x minus 2, and b we found to be 9. So we have plus 9 divided by x minus 2, and extra we have another c divided by x minus 1. C was found to be negative 4, so actually this is not a plus, this is a minus now. If we erase this, this is a minus. This is minus 4 divided by x minus 1. So that means that what we have on the left, when broken down into partial fractions, gives us 1 plus 9 divided by x minus 2 minus 4 divided by x minus 1. So therefore, this is the partial fraction expansion or decomposition of the rational function that we have on the left hand side. This is how we do partial fraction breakdowns. Often the method that we use is comparing x to the r term coefficients in this exact format. We just take the thing on the right hand side, we multiply it by the denominator, we take this thing, we multiply it by the denominator, and then we compare x to the r terms on the left hand side and right hand side, get a bunch of simultaneous equations which we then solve to find the constants that we defined here, a, b and c. So you'll note here the only real important things that we did were comparing the orders of the numerator and the denominator, subtracting them if this is an improper fraction, which in this case this is an improper rational function because the order of the numerator is greater than or equal to the order of the denominator, which means that other than the partial fractions we also have additional something on the left hand side here. And other than that, the only important things to note were that because the denominator was defined to not be 0 for the domain of the function, we could multiply by the denominator and be sure that we're not multiplying by 0. And when we did that, we got some equation on the left. The polynomial on the left is equal to the polynomial on the right, meaning that each of the corresponding coefficients was equal, meaning that we could compare the coefficients, get a bunch of simultaneous equations which we could then solve to find the constants that we defined up here. We found this a, we found this b, and we found this c. We'll do another one just to really get the point across, and this time we'll do an even more improper rational function. So we'll do, let's say, x to the 4th plus 2x squared plus x minus 1 divided by, let's say, x minus 1, x minus 2 and x minus 3. Let's try and do this one. So to do this one, the first thing we have to do is compare the orders of the numerator and the denominator. Comparing the two, this is order 4 and this is order 3 because there's 3 factors. So that means on top we have order 4, on bottom we have order 3, which means that if we have a whole part here, it would have to be order of 4 minus 3 or order 1. If it's order 1, it is of the form ax plus b. And then we have the partial fraction parts of this thing. In fact, to make the challenge a little bit greater, instead of writing this thing as 2 linear factors, I'll write this as an unfactorizable quadratic factor. So we'll say x squared plus x plus 1. So that means that writing the partial fractions, it will be plus and then some constant divided by x minus 1, because here the order of the bottom is 1, which means the order of the top has to be 0, plus something divided by x squared plus x plus 1. Recall, when we don't have nice factors, we don't factorize. This thing can be factorized into linear factors of x minus something and x minus something, but we don't do that, we just leave it as is. So if the bottom has order 2, the top has to be order 1 less than that, so order 1, which means that this is of the form dx plus e. Now if we write the left hand side and right hand side equal and the denominator is not equal to 0, we can just multiply by that, meaning that we have x to the 4th plus 2x squared plus x minus 1 equal to, then we have ax plus b times the whole thing of x minus 1 times x squared plus x plus 1 plus c divided by x minus 1 times this thing. Will have this x minus 1 term cut and we'll be left with c times x squared plus x plus 1, and we'll have dx plus e times, and when we multiply the denominator by this thing, this x squared plus x plus 1 term cancels with this one, leaving us with just x minus 1 product. So we have here x minus 1. Now I'm going to speed this up and quickly find the simultaneous equations that we need here. I'm also not going to solve this. I'm not going to encourage you to solve it either. I'm just going to show you how we would deal with something complex like this. So, ready? Alright, so this is the set of simultaneous equations that we need here. We have -1 is equal to minus b plus c minus e. We have 1 is equal to minus a plus c plus minus d plus e. We have 2 is equal to c plus d. We have 0 is equal to b. We have 1 is equal to a. So we already have 2 solutions actually. 0 equal to b, 1 equal to a. We have to solve these 3 simultaneous equations in order to get b, so c, d and e. So I'm just showing you this so that it can be done. I'll now quickly solve these set of simultaneous equations and give you the 5 constants. This is also going to be done really quickly. And I would also recommend that you yourself just draw some random polynomial on the top, divide by some random factors on the bottom, and try to do it yourself and see if you can resolve the partial fractions of this thing. Recall the orders of the numerator and denominator and how you would write the whole part if there is a whole part and the partial fractions. Alright, let's go again. Alright, so there we go. These are the 5 constants that we have here. We have a equal to 1, b equal to 0, c equal to 1, d equal to 1 and e equal to 2. So then substituting that into up here, we could write out what this set of fractions is. So we can say x square x to the 4th power plus 2x squared plus x minus 1. Hold on, let me quickly write that down. X to the 4th plus 2x squared plus x minus 1 divide by x minus 1 and x squared plus x plus 1 divide by x minus 1 and x squared plus x plus 1 is equal to ax plus b, where a is 1 and b is 0. So x plus 0, which is just x, and then we have c divided by x minus 1, c is 1, so we have 1 divided by x minus 1, so we have plus 1 divided by x minus 1 plus, and then we have dx plus e divided by x squared plus x plus 1. D was equal to 1, and e was equal to 2. So we have dx, which is 1x, which is x, plus e, which is 2, divided by x squared plus x plus 1. So this is the partial fraction decomposition of this scary looking polynomial on the left hand side, sorry, rational function on the left hand side. I would encourage you yourself to also try this. Just take any two random polynomials, divide one by the other, and recall the simple method. First thing you have to do, when you have px divided by qx, check, first step, I'll put number 1, is it proper? Because if the polynomial, one polynomial divided by the polynomial of the rational function is proper, it means that if it's yes, it means no whole polynomial part. What I mean by that is you don't have to write like some ax plus b in the front before doing c divided by something and d divided by something. That whole part can be skipped because this thing does not exist. So that's the thing that we want to check there. If it's proper, then we don't have any extra polynomial part on the left. We just have simply one number divided by a certain factor plus something else divided by some factor and so on. However, if it's not proper, meaning that there is something, then order of whole polynomial, I'm going to first quickly define this thing has to have order n and this thing has to have order m to make my writing simpler. The whole polynomial is equal to order n minus m, as we saw up here. Because the order here was equal to order 4 and the order overall here was equal to order 3, we had to have an order 1 whole part on the front, which is what we wrote down here. We wrote a whole part of order 1 ax plus b. It just so happened that b was equal to 0, but we cannot assume that. We need to write it down and then find out that b is equal to 0. So we have that. And then after this, the next thing we have to do is write down partial fractions where we have something divided by a factor, where if the factor is order k, then what we have on top is order k minus 1. We saw this above when we had a factor on the bottom of order 1. In this case, x minus 1 was order 1. The numerator up here was order 0 or just 1 minus 1. Over here, when we had a denominator of order 2, we had to have a numerator of order 2 minus 1 or order 1. So that's the second step. And then now that we have that, the third step after this is multiply everything by the denominator, or in this case I define denominator as qx, so we have to multiply everything by qx. And then the fourth step and final step, compare x to the r coefficients to form simultaneous equations like we just did. Simultaneous equations. And finally solve the simultaneous equations. And once you have solved simultaneous equations and found all the constants that you have defined, you can then take those constants, plug them into your original expression and write as a final answer. So in this case, my original expression was this: ax plus b plus c divided by x minus 1 plus dx plus e divided by x squared plus x plus 1. And then I substituted a, b, c, d and e and finally got my final answer. So I encourage you, take a random number generator on Google or something, just write down some random polynomial on the denominator like this. Just write some random thing here. Let's say x to the 4th plus 2x cubed minus 7x plus 3, and then write some other thing on the bottom, like let's say x minus 1 x squared plus 2x plus 4, something random like this. Just write something down and try to figure out what the partial fractions corresponding to this are. I promise you it's a good exercise. It will help you build a better understanding of partial fractions and be able to easily factorize polynomials and write the proper partial fractions. And remember, if we have a partial fraction that we could have the denominator factorized in some way where we don't get nice numbers, for example, if we have x squared minus 3 on the denominator, instead of factorizing this into x plus root 3 and x minus root 3, we tend to just leave it as x squared minus 3. It's just the way that we do things. So that is it. I would like to leave you with that and encourage you to do your own exercises to help you understand partial fractions and the breakdown of rational functions into their partial fractions. Thank you for watching and goodbye.